All right, here they give us a graph and they ask us several things. This is, I believe, actually out of 1.4, and this talks about one-sided limits. So this notation, the plus, means that we're looking from the right side. So as we're approaching the particular number, in this case 5, from the right side, what are we approaching? So as we start to the right of 5, and we come down our graph, as x gets really close to 5, we're getting close to this y value, which is 3. Hence, the answer 3. The minus here means what is our limit as we're approaching our value from the left side. So if we're to the left of 5, and we're getting closer and closer to 5 from the left side, what y value are we approaching? Well, that point that we're approaching has a y value of 3. And then the next part asks us, well, what is the limit in general? Well, for the limit to exist, these have to match. The limit from the right side and the limit from the left side have to be the same thing. So since from the right side we're going to 3 and the left side we're going to 3, then our limit is 3. If they are going towards two different numbers, then the actual limit itself would not exist. You might say, well, how does this exist and this not exist at times? This is just half of the limit. The definition of the limit says that we have to be approaching the same value from both sides. So this just tells us what is happening on one side. Question is the function continuous? So the definition of continuity says that we have to be approaching the same value from the left and the right. The limit has to exist. Let's list those. So the limit of the function as x approaches some value has to exist. So we've shown the limit exists. We're approaching the same value from the left and the right. The value of the function at that particular x value we're approaching, it must exist. And the limit as x approaches that number has to be the same as the value of the function. So what do I mean? Well, let's look by counterexample. If the limit exists, but the point is not, the function is not at the same location. So for example, if we put an open circle here, the limit exists. From both sides, we're approaching the same location, but that's not where our point is. This would not be continuous because we would have a hole, a gap in our line. To be continuous, from both sides, we have to be going to the same location, and there has to be a point where that's going towards. So if we're going towards the same location, and there's a point there, it's continuous, meaning there are no gaps, there are no holes. So in this case, yes, our function is continuous. We're approaching the same place from everywhere, there's a point there. So yes, we are continuous at x equals 5. Now what about this one? They ask us, what is the limit of this function if we call this function f? In this case, our c is 1. So if we're approaching 1 from the right side, if we're to the right of 1, then we're over here. So if we approach an x value of 1 from the right side, we're approaching a y value of -2. On the other hand, if we approach a y value of 1 from the left side, an x value of 1 from the left side, we're approaching a y value of 2. So down here, it looks like we're going to be at -2. Up here, it looks like we're going to be a +2. Since those are not approaching the same value from both sides, then that limit does not exist. We know where it's going towards, but the actual limit does not exist. And since the limit does not exist, since we're not going to the same place from both sides, it is not continuous. Is the function continuous at 1? No. Visually, that's easy to see. There's a break in the graph. It jumps from here down to here. So let's take a look at this one. It says find the limit. So by direct substitution, if we put a 0 for delta x, now this says for delta x, not for x itself, just delta x. So delta x, this whole thing is a single expression. You could think of it almost as a different variable. So everywhere we have delta x, we're going to put a 0. So on top we have 8 over x minus 8 over x. Well, anything minus itself is 0. And on bottom we have 0. So that's indeterminate. So chances are that we may have a limit, so we need to see what it is. So we need to figure out what is a way that we can rewrite this to make it no longer indeterminate. Well, if we have a fraction on top, we can combine those. So let's see, how are we going to combine 8 plus delta x minus 8 over x? Let's just leave the denominator off for now. So how would we put those together? Well, to subtract fractions, we have to have a common denominator. That's one denominator. This is another denominator. So if we're getting our least common denominator, remember a least common denominator is a common multiple of both of these. So we can't simply just add delta x on top and bottom. That doesn't work. We can multiply top and bottom by the same thing, but we can't add top and bottom by the same thing. That doesn't maintain equivalence. So to be a common multiple of x plus delta x, we have to have that factor. So that's one factor, that whole thing. To be a multiple of x, we have to contain a factor of x. This does not contain x as a factor. It contains x as a term, something that has addition with it, but this doesn't contain x as a factor, something that is being multiplied by. This is not delta times x. Delta just means a change in x. So if we're going to be a multiple of this denominator, we have to have that factor also. So this is going to be our common denominator, x times x plus delta x. So we're going to rewrite both fractions using this common denominator. So for the first fraction, we already have the parentheses on bottom, so we need to pick up an x on bottom, and if we multiply the bottom by x, we multiply the top by x. The second fraction already has an x on bottom. It needs to get an x plus delta x, so we have to do that on top and bottom. And if we distribute, we would have 8 times x, 8 times delta x. Now that we have the same denominator, we can keep the denominators and we can put the numerators together. So we're going to have an 8x minus 8x minus 8 delta x. Remember, when we're subtracting fractions, that minus applies to each term on top. So minus 8x minus 8 delta x. So the 8x's cancel. So when we combine the terms on top, we get minus 8 delta x over x times x plus delta x. So that's 8 minus 8 delta x over x times x plus delta x. All is over delta x as delta x goes to 0. This is still indeterminate. We would still get 0 on top, 0 on bottom. But this is a complex fraction. We can think of the denominator as being over 1. Instead of dividing by delta x, we can change this to multiplying by the reciprocal, which would be 1 over delta x. And in that case, the delta x's cancel. We've not taken the limit yet. All we've done is algebra. Now we have a minus 8 on top, x times x plus delta x on bottom. Notice the delta x being on bottom is what made this undefined, because if we replace delta x with 0, we had a 0 on bottom. Now that that delta x on bottom is gone, if we directly substitute 0 for delta x, we get x times x plus 0 on bottom. X times x is x squared, so that's our limit. We let delta x go to 0. We did not let regular x go to 0, so we still have an x in our limit. We just don't have a delta x in our limit. So that one was a little bit trickier, but it's important that we differentiate between an x and a delta x, and letting delta x go to 0, not letting x go to 0. All right, this one asks us to discuss the continuity of this function. And if we just simply look at this function, to see where it's not continuous, if it's just a regular function, where it's not continuous is anywhere that it's undefined. So if we look at x plus 3 equals 0, why do I do that? If we have a fraction, the denominator cannot be 0. So this fraction is defined everywhere except where the denominator is 0, or wherever x is negative 3. So it's discontinuous at x equal negative 3. It's continuous everywhere else. If it asks where is it continuous, it's continuous from negative infinity approaching negative 3, and negative 3 to infinity. If we were to look at the graph, notice at negative 3, it's not an asymptote, it's a hole. We have a hole in the graph there. This is not part of the question again, but let's look at the limit. If we were to take the limit of this function as x approaches negative 3, negative 3 squared, negative 3 times negative 3 is 9. So this would be indeterminate. Indeterminate. If we factor the numerator, we would get this. Remember what we said about if it's indeterminate. To be a vertical asymptote, we would have to have a 0 on bottom, but not 0 on the top. Hence, this is not a vertical asymptote. It is undefined at negative 3. X cannot be negative 3. But since we don't have 0 on top, it's not a vertical asymptote. In this case, it's a hole. Notice this fraction reduces. The x plus 3's cancel. And if we replace x with negative 3, we get a limit of negative 6. So while this function is undefined at negative 3, as we're approaching negative 3, in the x direction, we're approaching negative 6 in the y direction. So that's our limit. Since those can cancel out, this is referred to as a removable discontinuity. A removable discontinuity. Why is that? If we compare our original function to the function x minus 3, since this function came from reducing the original function, these two functions are equivalent, except the top function is undefined at negative 3, the bottom function is not undefined at negative 3. So we got rid of what made it discontinuous. We got rid of the part that made it undefined. So we removed the discontinuity of -3. So when it later asks about removable discontinuities, that's what we're talking about. If it's discontinuous at a place, if at a certain x value we are undefined, but we can do some algebra to make that discontinuity go away, now we have a function that's no longer discontinuous. Those are the same everywhere except that. That is a removable discontinuity. They have the same limit. They both have a limit of -6. Okay, this one asks us kind of some similar things. They don't give us a picture, but they ask us, where is this not continuous? So this would not be continuous if the denominator equals 0. Everywhere else it's continuous. So if we add x squared to both sides, take the square root of both sides. Remember, if we take the square root of both sides, we have to include plus or minus our square root. So when x is 3, 3 squared is 9, we would get 0 on bottom. When x is -3, -3 squared is 9, 9 minus 9 is 0. So both of these make our function have a 0 on bottom and make it undefined. So these are both discontinuities. These are both places where we are not continuous. We could also look at that denominator as 3 minus x, 3 plus x. So one part of the question is, which of these are removable? Well, can we get rid of either of those factors? Does this fraction reduce? And the short answer to that is no. We have a factor of 8, or that could break down on top, but that's not going to reduce with either of those. So we're not able to get rid of what makes it discontinuous. So both of these are non-removable. And when they're non-removable, in a rational expression, these are vertical asymptotes. 0 over 0 is a whole, and that's removable. Something else over 0 is an asymptote, and that's non-removable. For the next problem, this is a piece-defined function instead of just a regular function. So to determine where it's not continuous, we're looking for discontinuities. So for a piece function, we can have discontinuities a couple places. We can look at each piece separately and say, for the first part of the function, f of x equals -6x, is it ever discontinuous? Is that ever undefined? And the short answer to that is no. That's not discontinuous ever, especially on that interval, but that is always defined. That's never undefined. If we look at the second part, x squared minus 7x plus 7, same thing is true there. That's a polynomial, so that's not discontinuous. Any number you pick for x, you're going to get an answer for that. Now, the top function only applies when x is less than or equal to 4. The bottom part only applies when x is bigger than 4. But regardless, we know that top function is always continuous. The bottom is always continuous. So does that mean the function overall is always continuous? And the short answer to that is no. We have to look at where do they come together. These two curves come together at 4. So in order for it to be continuous, when we're to the left of 4 and when we're to the right of 4, those two pieces have to come together at the same place. In other words, when we take the limit of our function approaches 4 from the left side, and when we take the limit of our function as x approaches 4 from the right side, those have to be approaching the same value. there is a point where they come together. There is a point where x equals 4. So those two have to join at that point where x equals 4. So we need to take those limits. So how do we take those limits? When we're looking to the left of 4, notice the top interval applies when we are left less than 4. So we're going to use the function negative 6x. Let's see, let's not do it like that. So the top one, we're taking the limit of negative 6x as x approaches 4, and that happens to be from the left. So if we put a 4 in for x, negative 6 times 4 is negative 24. So for the top function, as x is getting closer and closer and closer to 4, the y value is getting close to negative 20. We're approaching x from the right. Our formula is x squared minus 7x plus 7. And again, that's when we're approaching 4 from the right side. So what is that approaching? Well, that's approaching 4 squared minus 7 times 4 plus 7. So that's 16 minus 28, what's that? Negative 12 plus 7, which is negative 5. So these are not coming together. From the left side, as we're getting closer and closer to 4, we're approaching negative 24. So this would be 4 and negative 24. On the right side, when we're getting closer and closer to 4 from the right side, we're approaching negative 5. So we're approaching two different y values. So there's a gap there. We're coming to two different locations. So A, the limit does not exist. And if the limit does not exist, then it's not continuous there. So it is discontinuous at x equals 4. The two portions of the graph do not come together. Now, if we were to graph this, the right portion technically does not include x equals 4. So we would have an open circle there, a closed circle here. But nonetheless, they don't come together. So it's discontinuous at 4. Continuous over here, because that part is a straight line. It's never going to be undefined. Continuous over here, because this is a parabola. That's never going to be undefined. Discontinuous here, because they don't join. Now we have one more problem. And on this one, they want us to find what number we get here so that this function is continuous on the whole number line. So notice the bottom part, if we think about this as two different functions, 9 sine x over x and a minus 6x. This is never going to be undefined. Regardless of what constant we have here, we can take a constant and subtract anything from it. We're not going to end up dividing by 0, and we're not going to have any square roots that are negative, so nothing is going to make this undefined or imaginary. So this is continuous on its entire interval. The only place that the top one would be discontinuous is at 0. We can't divide by 0. Well, if we look at its interval, 0 is not part of its interval. So this is everywhere on this interval, this is defined. Everywhere to the left of 0, we would get an answer regardless of what we plugged in for there. And from 0 to the right, we would get an answer for this. So the only place that it could be discontinuous is at 0. So let's see what happens at 0. So to be continuous, the limit x approaches 0 from the right of our function, and the limit as x approaches 0 from the left, those would have to be equal. So for what does a need to be? We take the limit, x 0 from the right. Well, if we're to the right of 0, we're using the formula. A minus 6x. And then if we're to the left of 0, we're using the top formula because this is to the left of 0. The limit of the left one. We let x go to 0. A is an unknown constant. If x goes to 0, 6 times 0 is 0, so we get A on this one. For the other limit, if we let x go to 0, that part goes to 1. Sine x over x, that goes to 1 as x goes to 0. So we get 9 times 1, or 9. For us to be continuous at 0, those two limits have to be the same. They have to come together. So we have to equate those. So A would have to be 9. The left limit and the right limit have to be equal. For them to be equal, this limit is A, this limit is 9, hence A equals 9.